So it's my pleasure to introduce Caleb Swan from University of British Columbia, who will speak to us about flows of G2 structures associated to Calabi-Yau manifolds. So please, Caleb, whenever you're ready.
All right. So firstly, I'd like to thank you, Professor Sheets, for inviting me to talk about this. I really appreciate it. So as advertised, I'll be talking about flows of specific G2 structures that we can that come from some Calabi-Yau manifolds. So as an overview, what the goal of this talk and what we did was we were trying to establish a correspondence between two particular flows. We have the Laplacian flow in G2 structures and the Laplacian coflow in G2 structures. And we're trying to establish correspondences between these flows and some flows on the base, where we take the base as a Calabi-Yau 2 manifold or a 3 manifold and cross in some tori. And this work was done with my PhD advisor, Sebastian Picard. So more specifically, I'll just flash the main results that we had is that if we start the Laplacian flow with some initial data, so the Laplacian flow of G2 structures, this phi is the G2 structure, and we can see it depends on this omega, this scalar form, and this upsilon, which will be our holomorphic volume form in either case. Then this entire flow for this Laplacian flow exists and is given by some flow on the base, and it converges to some stationary point. We'll get more into the details of all this later, but just to flash the results really quickly. And then we have a similar thing with the coflow, where instead of the flow we had before, we're flowing along the base with the Kähler-Ricci flow up to some diffeomorphism. So an overview for how this talk will go. We'll quickly get what we need from the machinery of Calabi-Yau manifolds, and then we'll introduce G2, the group G2, talk a bit about G2 structures, and then describe how we can obtain G2 structures from Calabi-Yau manifolds. What we're doing is a pretty trivial case by just considering crossing in some tori, but there are more generalizations of this that can be looked at. Then we'll get into the meat of the Laplacian flow and how it corresponds to the flow below. Same with the coflow. And since the result had something about points at infinity, we'll talk about how this flow converges and the limits as we take time going up to infinity. Okay, so starting with Calabi-Yau manifolds, we'll take our definition. Everything that the manifolds that we'll be working with are all going to be Kähler, and we're implicitly just going to assume that they're all compact, so everything's good. We will take our definition of Calabi-Yau to be complex with dimension n, and it has a Kähler metric and a nowhere vanishing holomorphic n0 form upsilon. So one thing is compared to the preprint where I denoted this by big omega, it's probably easier to denote by speech omega and upsilon instead of big omega and small omega. So that's just a cosmetic change, if anything. I'll refer to the pair omega and upsilon as a Calabi-Yau structure for ease. And what we know from this, if we have this existence of the holomorphic volume form, then we have the canonical bundle is trivial. The first Turing class is going to vanish, and we have the Ricci form given by this potential log of the norm of upsilon with respect to omega. This vanishes if and only if this norm is constant. So we'll talk quickly about Yau's theorem. So we are working on a compact Kähler manifold. We have an existence of a Kähler structure, and the existence of the holomorphic form tells us that we have the first Turing class vanishing. So Yau's theorem, which is given here, implies the existence of a Ricci flat Kähler metric in the cohomology class. This is sort of the nice one that we like. This metric's unique in the Kähler class, and in our case, I'll just refer to it as a Calabi-Yau metric. And the way that Yau's theorem has been proven, at least one way, is solving these complex Monge-Ampere equations, and these have been studied extensively. What we want to do is look at these complex Monge-Ampere equations involving the determinant of omega plus I del bar of some function, and see where that gets us. So more recently, we have these Monge-Ampere flows. So these have been studied by Sebastian and Xiangwen Zhang. So what they do is that we work on a compact Kähler manifold. doesn't have to have first Chern class vanishing, but in general can work. And if we have a function going from the manifold to the reals and a smooth function that is strictly increasing, then we have solutions to this parabolic complex Monge-Ampere equation. So you can see the determinant of omega plus del del bar u. What this gets is that for all time, we have evolving metrics. So if we start with some initial condition omega, we get these omega tilde t's that we by just adding I del del bar of u. So this family of metric will exist. It exists for all time and it converges in each CK norm to some limiting metric in the cohomology class of the original thing. Importantly, for this flow, the complex structure that we start with stays fixed throughout. And in our case, when we are working over Calabi-Yau manifold, the limiting metric is the unique Ricci flat Kähler metric, the Calabi-Yau metric. This class of Monge-Ampere flows is sort of a generalization of other classes that flows that have been studied. So it's a generalization of the Kähler-Ricci flow and the anomaly flow. All you have to do is take the functions h and a appropriately. So for the Kähler-Ricci flow, if we take h to be log and a to be something appropriate that sort of fixes and allows it to scale. Same with the anomaly flow, we can take h of rho to be rho. These Monge-Ampere flows sort of encompass all these other flows. And for us today, we have two particular cases that we care about. We have this MA 1/3, Monge-Ampere 1/3 flow. Well, we called it this because of this 1/3 appearing in the definition of H. H is really just rho to the 1/3 multiplied by some constant. And we have the Kähler-Ricci flow, where we take H is 2k times log rho. Again, these don't match, but everything up to scaling is sort of good. And what do we get from these Monge-Ampere flows? We have pretty much the same estimates as we have for the Kähler-Ricci flow and other things. So we have uniform estimates. So these are uniformly bounded, where the GTs are the evolving Riemannian metrics. They are uniformly bounded by with respect to the starting metric, and we also have good bounds on their derivatives. And we also have exponential convergence of this flow. So all these estimates exist for the Kähler-Ricci flow. So in that case, the top lines they were proven by Chow, and then the second one they were proved by Fong and Sturm. Whatever happens there basically happens for the more general class of flows. Okay, so that's all the machinery that we sort of need from Calabi-Yau manifolds. Now we'll quickly talk about G2 structures and where those come from. So G2 structures really can be thought of as coming from the octonions and more specifically the imaginary octonions. As a vector space, we can think of the imaginary octonions as isomorphic to R7. So those structures sort of get ported in over. So as stated here, we'll let O denote the octonions, and we can consider the commutator and the associator of octonions. Since the octonions aren't commutative and they aren't associative, these two operators are non-zero. What happens is that it turns out that these forms these operators allow us to define a 3 form and a 4 form just by combining the associator with the inner product or the commutator with the inner product. And when we restrict our attention to just the imaginary octonions, these are completely skew symmetric in all of their inputs. So they do define a 3 form and a 4 form. We also get this octonionic cross product by just taking regular octonionic multiplication and projecting onto the imaginary part. These are the structures that we get from the imaginary octonions that we would like to port over into R7. So by just regular identification, we can really have all these structures on R7. So we'll call this the standard G2 structure. So for that, we have the Euclidean metric, we have the standard orientation and standard volume form, we have this 3 form that we got from the commutator, we got the 4 form from the associator, and the octonionic cross product. You can check that in actuality, the 4 form is really determined by the 3 form and the Hodge star that we get from the metric and the volume form, and the cross product is also determined from the 3 form. And we'll define the group G2 as the subgroup of GLR7 that preserves the standard G2 structure. So that preserves all these bullet points over here. Life can actually be a bit simpler. It was shown by Robert Bryant that the metric, the three form, and the volume form are actually just related by this this identity over here. So if we take two vectors and hook them in and take appropriate wedge products, we get basically just the inner product of two vectors. Since so the three form really determines the metric and the volume form, and the metric and volume form really determine everything else with the three form. So we get a much simpler definition. As long as we preserve the three form, we preserve all the structures. So G2 has a much more simpler definition by given over here. To bring this onto manifolds, we basically do all this linear algebra that we did at a point as vector spaces at every point in the manifold. So on a manifold, as long as if we have a three form that satisfies this equation, so this over here is very akin to this one over here. We expect what comes out to be sort of an inner product. So if we take the same vector, we should get something non-zero. If that's true for our three form, then we can define a metric and a Riemannian volume form by using that same formula over there. So we get a Hodge star, and then we get a dual four form, and we also get a cross product. So all the structures come from this three form again. As a notational thing, some authors do put a plus sign instead of a minus sign. All it does is change the orientation. Yeah, and so we have characterizations of what 7 manifolds emit G2 structures, and that characterization is if it's spinnable and orientable, then we have a G2 structure, and that's an if and only if. There's another way we can also think about it equivalently as the reduction of the frame bundle to the group G2. But we'll take the more concrete definition, I guess, by just looking at the three form. So from that, we can decompose our spaces of forms into irreducible G2 representations, and this will allow us to define the torsion forms in one way. So if we take the exterior derivative of the three form and the exterior derivative of the four form, it turns out that we can always write it as such, where tau 0 is a function, tau 1 is a one form, and tau 3 is a three form. So the Hodge star of a three form is a four form. This all checks out. And tau 2 is a two form over here. So these are of the correct degree. The tau 1s over here are indeed the same form. That can be checked. There's proof in some of the literature out there. But what this gives us is we have 4 independent torsion forms, so, which allow us to define classes of G2 structures. So with the 4 independent torsion forms, they can either be 0 or non-zero. So with 2 choices each, we get 16 classes. And we will care about 3 of them today. We say we care about closed G2 structures. That's when the three form is closed, which equivalently means that tau naught, tau 1, and tau 3 are 0. We have co-closed G2 structures where the four form is closed. In that case, tau 1 and tau 2 both vanish. And we have torsion-free if both of these hold simultaneously. And the torsion-free G2 structures are sort of the ones we care about. Those are the ones where the metric obtained by the G2 form, if we take the Levi-Civita, we can get the Levi-Civita connection, and the three form is parallel with respect to its Levi-Civita connection if it's torsion-free. We also get that the Riemannian holonomy of the metric is contained in the G2 and in the group G2, and the metric is Ricci flat. So the torsion-free G2 structures are sort of the ones that we care about in that sense. Okay. So now that we have an idea what G2 structures are, we can talk a bit about the Laplacian flow and the coflow. And these are the 2 flows that we will look at in more detail. So the Laplacian flow, this was introduced by Robert Bryant, and what it does is that at every point in time, we change the three form by its Hodge Laplacian. So the right-hand side is secretly nonlinear in the argument. Remember that the Hodge Laplacian is d star plus d star d, and those stars are obtained by the metric and the volume form, but the metric and volume form are defined in some nonlinear fashion by the three form. So this right side over here is nonlinear in the argument. But we can see that the critical points of the Laplacian flow are torsion-free G2 structures. In the compact case, this can be shown by a quick integration by parts argument, but it holds in general. One thing that we tend to do to make things easier when we study Laplacian flow is to just restrict our attention to closed G2 structures. When we start with a closed G2 structure, we can see that we're sort of flowing by an exact piece every time. So it actually stays within the cohomology class. It's a much harder thing to look at the Laplacian flow when from an arbitrary starting point. And I don't think very much has been done on that from that front. But when we restrict our attention to closed G2 structures, we have some very nice properties of the Laplacian flow. We have good estimates of norms of the tensors and all that. And the important theorem we have from Brand and Ricci is that the Laplacian flow has short time existence and uniqueness when restricted to closed G2 structures. So that's the theorem down below. And that was proven by using a de Turk trick and some Nash-Moser and Hamilton inverse function theorem. We also have the coflow, which is very similar, but instead of flowing the 3 form, we flow the 4 form. So we have a 4 form over here, and we flow it by its Hodge Laplacian. So if we have the 4 form, we can always reconstruct the 3 form, although the only thing is that the 4 form itself doesn't determine an orientation, which is one caveat with this flow. So what we can do to fix it is that from our initial condition, we can fix an orientation and set that orientation to be fixed along the flow, and that solves any of the issues. But this flow was first introduced by Karagiannis, McKay, and Choi, but they put a minus sign on it to make it analogous to some heat flow. But we will do without the minus sign. And like the Laplacian flow, its critical points are torsion-free G2 structures. In the compact case, integration by parts will do that, but this also holds in general. And we generally restrict our attention to co-closed G2 structures in the same way. Right? Here we're flowing by some exact piece. We're flowing the 4 form by some exact piece. So we stay within the cohomology class of the 4 form instead. Everything else is pretty analogous to the Laplacian flow, but the only thing is that unlike the Laplacian flow, we don't have short-time existence and uniqueness. The proof method that Brian and Shu used doesn't hold up exactly. What we get when we try and do the same thing is that we get some extra term that is some obstruction in some sense. So there's a modified Laplacian coflow that adds the extra term away. That one has short-time existence uniqueness, but it introduces new critical points instead. Now that we've talked about Calabi-Yau manifolds and G2 manifolds, and we talked about their flows, we'll look at how to go from one to the other. So given a Calabi-Yau twofold, that's real dimension 4. If we want to get a G2 structure, we have to add 3 dimensions somewhere. To do that, we'll cross in a 3 torus. We're crossing in torus to keep compactness instead of crossing in R3, for example. But if we do that, and if we're given a nowhere vanishing complex function on our base manifold and a strictly positive function on our base, we can define a G2 structure on this product in this form. So what we're doing is taking the 3 angle coordinates and then pairing the angle coordinates with each one of these self-dual forms, right? Omega is self-dual, the real part of upsilon is self-dual, and the imaginary part of upsilon is self-dual, right? These are sort of the 3 hyperkähler structures, I guess. Anyway, this gets us our G2 structure. You can check everything in coordinates, and if we do so, we can also compute what the metric looks like and the volume form and all the other things. So if we do that, we can see that we get this sort of warped product, right? We can see that R1, the angle coordinate R1 is sort of distinguished from the other two. It has a different coefficient in front of them. R2 and R3 have the same coefficient as the base manifold. We can also get the volume form, we get the Hodge star, and the dual 4 form. All of these are computed as such. The factors of 2 that show up are not really very important. They're just sort of a byproduct from going from the Hermitian metric to the Riemannian metric, right? Because the G2 structures are sort of done on something real, whereas the Hermitian is coming from something complex. So that adds the factor of 2 everywhere. For the 3-folds, we can play the same game. Instead of crossing in a 3 torus, we just need 1 extra dimension, so we cross in an S1. So if we have a same nowhere vanishing complex function and a strictly positive function, we can define a G2 structure in the same way. Here we pair the 1 angle coordinate with omega, and then we take the real part of the holomorphic volume form. That gets us a G2 structure. And we can compute the metric and volume form in the same way. Again, we get this warp product. dr squared has this different coefficient in front of it than the G6 metric on the base. So now that we know how to go from Calabi-Yau structures to G2 structures, we can talk about what happens when we flow structures that we get from there. So if we start with the Laplacian flow, as mentioned before, we like to restrict our attention to closed G2 structures. So we need to pick F and G in a nice way that does so. In particular, if we pick F to be this norm of upsilon with respect to omega and G to just be the constant 1, then we get these G2 structures. So on T3 cross the Calabi-Yau twofold, we get this, and on S1 cross X6, we get the other one. Since both omega and upsilon are closed, we can see that these forms are indeed closed on the product. And for the Laplacian flow, we need to care about the Hodge Laplacians. By just computing them, we can see that they arise from these Lie derivative terms. The vector we're taking the Lie derivative to is some gradient of the norm to minus 2/3 in both cases. And we're taking the Lie derivative of things that look similar to the terms that make up the G2 structure. Right here we have 2 RD1 wedge omega minus dr2 wedge real part upsilon minus dr3 wedge imaginary upsilon. It's very similar to what we have up here, except the signs are a little bit different. We can also look at the torsion. So like we said, our goal is to sort of look for torsion-free G2 structures. Well, in a sense, we know what the torsion-free G2 structure should be if we start with the Ricci flat one. But if we don't start with a Ricci flat G2, if we don't start with a Ricci flat Kähler metric, we can still compute what their torsion forms are. Since we have a closed G2 structure, we expect tau naught, tau 1, and tau 3 to vanish. It turns out tau 2 is pretty much the exact same thing that we had for the Hodge Laplacian, except instead of the Lie derivative, we're taking an interior product. And that just comes out because this Hodge Laplacian is just the exterior derivative of this, and we use Cartan's magic formula to go from the interior product to the Lie derivative. And in both cases, it's pretty much looks like the exact same thing for the respective ones. And we know that the torsion forms will vanish if and only if that norm thing is a constant, or equivalently when we start with that Ricci flat Kähler metric, like I mentioned. In any sense, we can start plugging everything into the evolution equations. We know that if we assume we are preserving the ansatz, as in if we assume that the Laplacian flow preserves the type of G2 structures that we are starting with, then we get these evolution equations. How the 3 form evolves is just del by del t of this, and we know what the Hodge Laplacians are over here. All the t's down here are just to reintroduce the time dependence that we're looking for since we're looking at a flow. So just writing them out in both cases. And the idea to sort of simplify this, at least one thing that we can do is we notice that, well, we crossed in some tori, either S1 or T3. Those angle coordinates don't depend on time. They're just constant, so we can sort of throw them out. The other thing is that, well, we have terms involving big omega, we have terms involving omega and we have terms involving upsilon. They tend to not really interact too much, as in, well, we have dr1 wedge omega t here, we have 2 dr1 wedge omega t here with some Lie derivative, and then similar things for the upsilons. So if we consider them separately, here I've sort of colored them, right? The omega terms are in blue and the upsilon terms are in red. We can see that from the left-hand side to get to the right-hand side, all we did was multiply the omega terms by 2, hit it with the Lie derivative, and multiply by some constant at the start. These are different for the different dimensions, but basically the same thing. And for the upsilon forms, all we did was switch signs, then hit it with the Lie derivative, and then multiply by that same constant. So sort of taking those apart and recombining the cases, right? In the T3 cross X4 and the S1 cross X6, this behavior is sort of the same, right? The upsilons get multiplied by -1 and the omegas get multiplied by 2. So we can sort of unify both cases together, and we'll let H denote the metric in either case. If we match the terms with the omegas and the terms with the upsilons, this is basically what we get, right? For the omegas, we multiply by 2, hit it with the Lie derivative, and multiply by some constant, and same with the upsilons. So k is just some constant that depends on the dimension of the base. And if we can find structures that satisfy these two coupled differential equations, then we know that the induced G2 structures satisfy the Laplacian flow, right? We got these from sort of just taking simplifications in some sense. The only caveat about this is that, well, we don't know how the top equation flows. Well, the top equation might have a solution and the second equation might have a solution, but we obtained our G2 structures from a Calabi-Yau structure, right? We had omega and upsilon being compatible, right? Omega being, sorry, upsilon being the holomorphic volume form with respect to the complex structure that we have from omega as well. So we need to worry about compatibility, right? These might flow in completely different directions and get us two forms that aren't compatible, so we don't get a G2 structure from that. So yeah, so a priori it's not clear that we have compatibility as this flow goes on. But we won't worry, as the solutions that we'll demonstrate are compatible because we get them in a way that ensures that. Well, we can still nevertheless look at the equations. If we sort of expand the first one out, we can see that how omega moves is sort of I del del bar of this norm term to the minus 2/3. All the t's there are just for time dependencies again. And if we look at, and we'll relate this top equation to the MA 1/3 flow. The second equation, if we expand this out and take a type decomposition, it actually implies that the complex structure should be changing. So this is a holomorphic volume form, so it's either 2,0 or 3,0, type 2,0, type 3,0. When we expand this thing on coordinates, we find that it's not purely type 2,0 or type 3,0, depending on the base. There's a 1,1 component showing up or a 2,1 component showing up, at least, which means that the complex structure needs to change so that we stay a holomorphic volume form with respect to whatever thing. Which is also sort of why that I added this T over here for the del bar, right? If the complex structure changes, then del bar changes in that sense. So in order to look at solutions, we know that the complex structure is changing, and we want to address compatibility. One thing we can do is try looking for solutions by just acting on compatible structures by moving family of diffeomorphisms. So this idea is similar to that of a paper by Fei, Fang, Picard, and Zhang. So let's try doing that. Let's look at a flow that's convenient. In this case, it's going to be the MA 1/3 flow. To do this, we'll fix some initial Calabi-Yau structure on our compact Calabi-Yau manifold. And if we run the MA 1/3 flow, we satisfy this complex Mondrian pair equation down here, and we get a family of Kähler metrics, omega t tilde, right? Just by adding I del del bar of ut, which is some family of functions that we get from the existence. These converge to the Calabi-Yau metric, as we've mentioned before, and the complex structure with respect to this flow stays fixed, right? So J is constant. If we compute del del bar of the omega tildes, well, those are basically just how ddt of I del del bar of ut from what we constructed, and we can compute that this really is sort of the term that we're looking for, right? It's very close, right? I del del bar of this norm to the minus 2/3 is very similar to this equation over here that we're looking for. So it tells us that we're on a good track so far. Now, we still haven't addressed the fact that the complex structure needs to change, so let's do that. So we've defined these auxiliary structures, omega tilde. Those are Kähler structures with respect to some fixed initial complex structure, and we can use these Kähler metrics to define a time-dependent vector field just by taking the gradient of that norm to the minus 2/3. That time-dependent vector field will then determine a one-parameter family of diffeomorphisms that are isotopic to the identity. And we can take those diffeomorphisms and pull our tensors back. So we'll define omega t to be the pullback of the auxiliary structures, omega tilde. And then we can just pull back our initial holomorphic volume form. We can pull back our initial complex structure, and then the Riemannian metric will follow with the Kähler metric, right? So we have that omega tilde, upsilon, and j are compatible as Calabi-Yau structures, and then pulling them back, we have that omega t, upsilon t, and jt are compatible as Calabi-Yau structures. So that satisfies the compatibility problem. Now we just have to make sure that we satisfy the evolution equations that we care about. So using this computational thing in the Turk's trick, we can actually show that, right? So checking how del t of omega is, well, we know omega is the pullback of the omega tildes, and then just computing, and by the choice of the vector field y, we get what we want, right? Over here, this lead derivative term, we've shown that this is pretty much I del bar t, so we cancel out to get the right coefficient of what we want. Similarly, we can do the same thing with the holomorphic volume forms, how they change using the same computational trick from de Turk's trick, and we get the evolution equations that we care about. So as a quick summary from what we've looked at with the Laplacian flow, well, we just really need to look at the base and flow the structures on the base by the MA 1/3 flow and pull back by some diffeomorphisms, and we solve the Laplacian flow. Right, so all their associated G2 structures are good because the flow on the base preserves the compatibility conditions that we care about. And this is we've demonstrated a solution to the Laplacian flow, and we have uniqueness of the Laplacian flow. So the solution is unique given the initial condition. For the coflow, we can pretty much do the exact same thing, except now we have to start with a co-closed structure. And to do that, we can just reverse our choices for F and G. We obtain these co-closed structures. Again, omega and upsilon are closed, so these structures are closed on the products. We can compute the Hodge Laplacians, and everything sort of looks very similar. The Hodge Laplacians are still lead derivatives of terms that make up the 4 form in this case. The only difference is that, well, the vector field that we're taking the lead derivative with respect to, instead of upsilon, norm of upsilon to the minus 2/3, we have log of the norm of upsilon. In either case, it still depends on that norm term, right? So if this norm term vanishes, then this vector field will vanish in the same way. You can look at the torsion forms. Torsion forms are going to be quite similar. Here we have that only the tau 3 torsion does not necessarily vanish, right? It's that interior product that we looked at. So these structures were co-closed, so we expect that tau 1 and tau 2 to be 0. Turns out that in this case, tau 0 is also 0. And again, torsion will only vanish if that norm is constant, or equivalently, if we start it with some Calabi-Yau structure. And then we can plug everything into the evolution equations, same idea. And the angle coordinates don't matter effectively. We can color and just match the terms involving omegas and upsilons. Here, the terms involving omegas, they switch signs, and the terms involving upsilons don't switch signs. There's no added coefficient going on. But either way, by picking out the terms, we get these coupled differential equations the same way. Right? They look very similar. In fact, they're basically the same, except that this vector field is different and this coefficient is different, but morally basically the same. And we can run the same thing. We still have the same compatibility issues, but as long as we work around those, we're good. So if we look at the top equation, it again tells us that we should be flowing something on the base. In this case, it looks like omega needs to flow by the Ricci flow, or some scaled Ricci flow. Okay, the Ricci flow. And the second equation again tells us that this complex structure needs to change, right? If we flow this holomorphic volume form, we don't get something that is type 2,0, type 3,0. So the complex structure needs to change. And we can use the same technique to sort of look for compatible Calabi-Yau structures. So this thing over here tells us that, hey, we should maybe be looking at the Kähler-Ricci flow. So that's what we'll do. We'll look at the Kähler-Ricci flow, we'll solve it, we'll rescale it for convenience. Well, not just for convenience, but so that all the coefficients work out. And that gives us some moving auxiliary structures, auxiliary Kähler structures. We can use those in the same way to define this time-dependent vector field, which gets us the one parameter family of diffeomorphisms. And then we can pull back all in the same way. So the entire method is pretty much analogous at that point, except we start with a different flow. If we do that, we can run the same computations, and this shows that it satisfies our coupled differential equations. Compatibility isn't an issue because we've already looked at that. And the coupled differential equations gives us solutions to the Laplacian coflow. So everything is nice and good. We come from the Ricci flow, we get a solution to the Laplacian coflow. The only difference in this case is that we don't have short time existence and uniqueness of the coflow, so we can't say that this is the unique solution to the coflow, although it's probably expected that it might be. Okay. So we've demonstrated some solutions, a solution to the Laplacian flow and the Laplacian coflow by just looking at things on the base, and these solutions exist for all time, right? The solution, the structures on the base, the flow on the base exists for a long time. So the solutions for the G2, for the corresponding G2 flows exist for all time. Now we just need to take a look at whether they converge and what limits we sort of get. So as a summary of what we've done so far, well, we have solutions to Laplacian flow and coflow in terms of things on the base. And in any case that we've done, whether it's a twofold case, threefold case, Laplacian flow, or coflow, our flow is really just solved by some pair of some Calabi-Yau structure, this pair omega and omega t epsilon t on the base, which is some pullback of some auxiliary structure on the base, and the pullback of the initial holomorphic volume form. The time-dependent family of the Kähler triples, they come from some Mongeon pair flow. We have two particular cases that it came from, and the Kähler metrics satisfy uniform estimates and exponential convergence conditions, right? Those came from the estimates at the start when we talked about Mongeon pair flows. And we know that they converge to the unique Ricci flat Kähler metric in the cohomology class in each CK norm. And the diffeomorphisms are, they come from a time-dependent vector field, and that's defined using some gradient of this norm thing, of this norm function. Well, not just the norm function, but log or this to some power. Right. With all these ingredients, we're going to look at convergence of our pair omega t epsilon t and the associated G2 structures, and we're going to borrow ideas from Lotte and Wei as they do so. They did something similar. So in order to do that, we want to take a look at these diffeomorphisms, right? The theta t's, we want to see what happens as t goes to infinity. In particular, we want to show that theta t converges to some diffeomorphism at the end so that we can pull back in the limit, basically. So let's take a look at how we can do that. Well, theta t was defined by yt. This is how yt is defined, and yt really depends on this norm function, right? It's either this norm to the 2/3 or this norm to the log of this norm. And the auxiliary structures, well, they converge to some Calabi-Yau metric. So this norm is going to converge to some constant thing. What this means is that the vector field yt is going to converge to 0 exponentially fast in each CK norm. So we have a good handle on its derivatives, right? It's bounded by this exponential term over here. And we want to sort of bring that bound to the maps theta. So for any 2 points in time, t1 and t2, we can define a path from theta t1 to theta t2 by picking a point, just by following the thetas. And when we look at the distance between those two, well, it's just the integral of this thing involving the derivative of theta, but the derivative of theta is what y is, and we have a good handle of y. So this at least shows that the maps theta t converge uniformly, and we can use the other uniform estimates because we have handles on derivatives of y, and those will eventually give us that uniform estimates and uniform estimates on theta t, right? So these are all going to converge in each CK norm, and this gives us some limit map as t goes to infinity. So at least at these converge to some map. Now we just need to check that it's a diffeomorphism. To do that, we need to get some sort of non-degeneracy of some sort. So what we can do is that we can take the ratio of the volume forms, right? So epsilon wedged epsilon bar, that's the volume form of our initial thing. And as we move epsilon t wedged epsilon t bar, that's the moving volume forms. If we take the ratio of that and take the log of that, that will get us some idea of how those compare to each other. And if we sort of follow this chain of equations just by taking just by using log laws and equivalences and moving the pullbacks accordingly, what we get is that we actually get this nice exponential handle on this term. So to get the bound on log of this thing, we integrate the thing that we just looked at, and we're integrating this exponential thing, which gets us a uniform bound. And ultimately what this shows is that, well, the pullback of the volume form is uniformly bounded with respect to the initial thing, and this pullback over here is the moving volume form. And ultimately that tells us that the map theta t, they're all uniformly non-degenerate. And we can push that to the limit to show that in the limit, it's the determinant of the pullback is uniformly bounded. We can pass that to the limit. So that is going to be a local diffeomorphism, right? At every point, the pullback is non-zero. So we get that's local diffeomorphism by the inverse function theorem. And then we can use properties of what we know about x and theta as well, right? Each theta t is a diffeomorphism, homotopic to the identity by definition. This gets that the limit map is surjective and also homotopic to the identity. And then our base is compact, right? We assume that our initial Calabi-Yau manifolds were compact. So the limit map is also a covering map. And then using that's homotopic to the identity, we get that it's going to be injective. So ultimately we have that the limit map is bijective, local diffeomorphism. So it's a diffeomorphism and everything works out nicely, right? So these structures converge to some pullback of the Ricci flat, the Calabi-Yau metric, and the pullback of the initial initial holomorphic volume form in the limit. So just applying everything back to the start, we can revisit what our main results were. Well, if we start the Laplacian flow with some structure associated to this G2 structure associated to a Calabi-Yau manifold, and we run the Laplacian flow, it's really just running the MA 1/3 flow on the base up to some diffeomorphism. And it converges to a stationary point that we've looked at, right? The stationary point is the pullback of the Calabi-Yau metric by some limiting diffeomorphism, and it's given by the pullback of the holomorphic volume form by some limiting diffeomorphism. And we get the analogous result for the Laplacian coflow, right? If we start the coflow, everything is done by running the Kähler-Ricci flow on the base up to diffeomorphism, and it converges to a stationary point given by some pullback of the Ricci flat Kähler metric on the base. And those will ultimately give us the torsion-free G2 structures on the product. All right. Okay, that's it. Thank you. Any questions?
Yeah, okay, thank you. That's interesting. I guess one thing I wonder is, yeah, like what if you try like a non-trivial circle bundle instead of just like Calabi-Yau cross S1?
Yeah, so we've been looking at that. So I guess we can do any like S1 principal bundle over a Calabi-Yau threefold. I guess it's easier to look at the threefold case because you're just crossing in one extra parameter instead of the twofold case where you have three extra dimensions. But
so sorry, you're saying that in that case you can prove the like convergence of the flow?
No, we haven't done that. We're looking at that yet. But so I mean, what we have is that we're either taking a twofold and crossing in three extra dimensions, or a threefold and crossing in one extra dimension, right? So right now, at least I'm looking at taking Calabi-Yau threefold, taking one extra dimension by taking some principal S1 bundle, right? So I guess what I've been told is the slightly easier cases to look at these contact Calabi-Yau 7 manifolds. So there's like it's sort of like a principal S1 bundle, except the way I've been thinking about it is that the derivative of the exterior derivative of the connection is the Kähler form in some sense. And similar things happen, except so far we know that and we're looking at the coflow. We're looking at it from the case of a coflow since it's more akin to the Kähler-Ricci flow. This tau naught no longer vanishes, so that's an extra complication. And if you run the Kähler-Ricci flow on, I guess, the distribution, it doesn't exactly match up. So we think that you have to modify the Kähler-Ricci flow to get what we want. But we haven't been able to see what exactly that modification needs to be, or whether we can write that out explicitly.
I see.
Yeah. So it turns out that the trivial case really hides a bunch of things, right? Like if you take something non-trivial, then there's something extra sort of hiding there.
Sure. Sure. Yeah, that makes sense.
Yeah.
I mean, there probably is some kind of like Yang-Mills flow portion for like for the principal connection. I mean, if you imagine it's like an invariant data on this 7-manifold, which is a principal bundle, there should be some kind of principal connection associated to that
Yeah.
data.
Yeah.
And
So maybe that connection might need to flow somehow as well
yeah,
to sort of
exactly.
get everything to be compatible, right? So
Exactly.
thinking of it as sort of just a fixed thing might not be the right framework, but
Mhm.
many things have to move in some sense.
Right.
Yeah.
Okay, yeah, thank you. Any others? Uh, okay, well, yeah, I'm gonna stop the recording.